Thanks for joining our presentation on the topic of BIM-to-Scan for Scan-to-BIM on generating realistic synthetic ground truth point clouds based on industrial 3D models. There are good reasons to investigate potentials in Scan-to-BIM. For one, the AEC industry is rather slow to adopt digital methods. Furthermore, most construction projects these days are brownfield projects, which means that they are based on existing structures. For those existing structures, there are rarely good and useful models available. This is where Scan-to-BIM comes in. We capture as-is conditions in the field and transfer this captured raw data into useful model information. To do that, we recognize objects in the captured data, find semantic segments, and much more. There are a couple of many data-driven approaches that show very promising results recently. The two citations shown on this slide are the ones that brought us the PointNet and KP-Conf architectures. If we want to apply such architectures and methods to our domain, we find that there is a big lack of ground truth and benchmark data. So we just don't have enough annotated point cloud data to apply to our domain. So the main motivation for this project is the shortage in data because the available amount and quality of annotated point cloud data that we can use for development and testing of our approaches is just too low. Although scanning equipment has become more and more affordable and well performing recently, the content of the scans that are done, especially in the industrial context, is so sensitive that it is rarely publicly available. Operators of facility fear for the secrets in the industrial environment and for the privacy concerns of their employees, and therefore rarely publish their data. To face these facts, we identified the opportunity of using 3D models because they are actually common practice across many industrial sectors. Last year, there was a publication shown here that showed the usefulness of synthetic data for applications of semantic segmentation, in which they used 3D models as just sampled points on their surface and could show a significant improvement of the precision of semantic segmentation networks. Furthermore, we decided to go with a more realistic synthetic data approach by using the simulation tool of Helios that was published in 2016. To put our approach into context, I would like to explain how it fits into our understanding of the digital twin concept. So we start from a real asset where we capture the actual as-is conditions using a laser scan, mostly. Therefore, we transfer the as-is conditions from the physical to the digital domain. With the resulting laser scan point cloud, we can then, depending on whether we have an existing model or not, use methods of scan-to or scan versus BIM to create or update a digital model. To close the loop and really make it a digital twin, of course, we need to enable the bidirectional flow of information and include the decisions that we make based on the information that is contained in our digital twin. Now we extend this rather comprehensive and well-known definition by our own, where we introduce the laser scan simulation into the loop. By doing a laser scan simulation on the 3D model that is part of our digital twin, we create the synthetic point cloud. And this, in turn, we use to develop methods of Scan-to-BIM and to test them, because this data, as I said, is much more easy to generate and much more cheap for us to get our hands on than the actual real laser scan point clouds. The toolchain we use for this is composed as follows. We start from a model authoring tool where we are not vendor dependent, where the actual 3D model of the facility is created. In this study, we have tried out Bentley MicroStation and Autodesk Revit for this purpose. We then, depending on whether we have semantic information in this model or not, use the IFC or FBX formats for model export out of the model authoring tool. This exported model is then imported into Blender, where we prepare the model for further steps. To be more precise, in Blender, we make sure that every model every object in this model actually is assigned with proper semantic information. If the original model had semantic segmentation already, this can be parsed out of the imported model automatically. If not, for example, if we have a pure 3D CAD model as an import, we need to follow up manually. We then export this model to a scene of wavefront OBJ files that can be directly imported into the laser scan simulation tool of Helios, where we perform subsequently the actual laser scan simulation. This results in a fully annotated ground truth point cloud, which means that every point comes with a class label, which is derived from the object that we prepared in the Blender application. After completing the toolchain, we wanted to make a comparison between the real and the synthetic data. To do so, we did a case study in an industrial facility and subsequently performed a laser scan simulation using the 3D model of that same facility. We used the same scanning locations and also adapted the same scanning parameters that the manufacturer provides for the equipment that we used for the laser scan. The figure in here shows a snippet of the real laser scan point cloud with RGB values as captured in the facility on the left, along with the result of our laser scan simulation, where the semantic classes are color-coded here in the right side. The comparison side by side shows a number of similarities, along with a couple of differences in the point clouds. What we can already see in here is, already in this high-level comparison, that we succeeded to introduce realistic occlusions into the resulting point clouds. In the next steps, we looked into the resulting data in a little more detail. To go into more detail, we chose a part of the model where our as-designed model and the real facility actually aligned quite nicely, which was not the case for all areas in this facility, unfortunately. On the left side, we can see the part from the real laser scan, and on the right side, we can see the corresponding parts from the laser scan simulation. While the real data has colors, shown here in the left snippet, we color-coded again the semantic classes in the laser scan simulation point cloud. I apologize for not using the same color code for the classes as in the previous slide, but the differentiation between the single classes should be clear. Now to actually investigate the point clouds, we calculated the surface density for both point clouds. And this is color-coded with the same scale for real and laser scan simulation point clouds. And we can see that our simulation tool does a quite good job in doing this point distribution per surface in a realistic manner. So we can see that the surface of the pipe that is facing the scan direction actually shows the highest density in points per surface, which is also, of course, what we would expect. Also, other surfaces that are not directly facing the scanning location show a much lower distribution of points, and the surfaces that face away and are hidden from the scanning location are actually occluded, as we can already see in this. Finally, we calculated the distance of cloud to model for both the real laser scan and the laser scan simulation. Of course, for the synthetic point cloud, so the laser scan simulation result, this results in a pretty uniform distribution, as the underlying model is exactly what goes into the simulation, and we used the same color scale for both evaluations. So the much more interesting result in this regard is the cloud-to-model distance for the real laser scan. What we can see in here is, for one, that the actual geometry of the facility as it is deviates from the as designed model in a couple of ways. For one, we can see that the second pipe run that is modeled in the lower right hand side is just not present in the real facility. In turn, we have this kind of secondary structures that holds this pipe run, which is just not modeled in our as designed model. Also, this pipe clamp and valve in the vertical part of the pipe are modeled very roughly only and in a slightly wrong location. Furthermore, we can see already in here that the geometry is approximated a little roughly in this as designed model, as we can see some deviations between the real point cloud and the as designed model, especially in the area of the pipe elbow. For a more detailed analysis, we reduced the data to the cross-section of the horizontal pipe from the previous slide, and then again investigated the cloud-to-model distance. We see that the circular cross-section of the real pipe is approximated by a polygon, which is straightforward because we used a triangular mesh in our as-designed model. What we can see, what is a little bit surprising, is this additional piece of the real laser scan pipe cross-section where we can actually identify that there's some pipe clamp that is just not modeled in our as-designed model. If we look at the histograms on the right side, where we overlay the real laser scan and the synthetic point cloud distances to model, we can see that the scanning parameters that we used in this slightly overestimate the actually achieved precision. And also we can see that this not modeled pipe clamp leads to a second small peak on the right tail of the distribution. Finally, to sum up our insights so far, we had a thorough literature research and identified that there's a high demand for label data. We identified Helios as a flexible, robust, and fast solution to create such ground truth data sets based on 3D models. But also we identified that the usefulness of the created data is definitely limited by model quality. To sum up, we find our approach to be a good intermediate step between sampling-based data generation and real laser scan point clouds, as shown below. As of now, we are using the synthetic data for training and testing with different neural networks for semantic segmentation. In the next step, we are testing approaches for semantic segmentation that have been trained purely on synthetic data on real laser scan point clouds. Then we also want to compare our results that we can get through this, of course, through the already known sampling-based methods to quantify the performance. And then we also want to investigate the influence of training on combined datasets with real and synthetic data. As an outlook in here, in the right side of this slide, we included some first preliminary rough results. On the very right, we can see label predictions on testing data taken out of synthetic data for a network that was trained purely on synthetic data, which shows quite nice results. And in the middle of this slide, we can see the prediction results for real laser scan data, again, for a network that was purely trained on synthetic data. We can see here that it's, of course, not as clean as the results for the synthetic data, but yet promising. And we definitely look forward to find out more about this and also to present further results, hopefully soon. Here are the references that I used throughout this presentation. And also I want to acknowledge our partners at Audi who have been supporting this research project. Thank you for your attention, and I'm happy to answer any questions.